Hey, what's going on? Today we're going to be looking at the properties of ionic and metallic bonds. So just to recap, the type of bonds we've looked at include the three following. In the last unit, we talked about covalent bonds, and that's when atoms are sharing electrons, which can be shared equally in a nonpolar bond or unequally in a polar covalent bond. In this unit, we're going to be looking at ionic and metallic bonds. You can see ionic bonds are when atoms gain or lose electrons. Metallic bonds are just the attraction between metal atoms and their surrounding sea of electrons, which we'll be looking at further in just a few slides. So the metal and nonmetal atoms combine to form an ionic bond. Two nonmetal atoms combine to form a covalent bond. And when metal atoms bond together, that forms what's called a metallic bond. So let's look first at the properties of ionic bonds. The bond formation, we've seen lots of examples of this. The classic example is sodium and chlorine, the love story between those two. And what you see is sodium, or any metal, is going to give its chlorine atom, the nonmetal, any nonmetal, its valence electron or valence electrons, and just completely transfer those over, which makes sodium here now positive, what we call a cation, and chlorine negative, which we call an anion. And so both of these ions are why we have an ionic bond. Once one's positive and one's negative, this attraction occurs and they're bonded together. And this attraction continues with lots of other positive and negative atoms, and you end up forming what you see here. This shape is called a crystal lattice. So this lattice structure of ionic bonds exists because you have the alternating positive and negative. So this is what solid salt would look like as a crystal. Ionic bonds usually take solid shape. You can see here an example, table salt, another classic example. All solid. And their melting point is extremely high. Ionic bonds, because of that strong attraction between the opposite charges, does mean the bond is pretty strong. So you can see in Celsius here, these values are very high for these ionic compounds. Ionic bonds are also soluble in water, which means they are dissolvable in water. You can see when that salt crystal, the sodium chloride solid, drops in water, the polar ends of water attach to the oppositely charged atoms making up the sodium chloride crystal and break it apart and just start ripping it apart and pulling those apart. And you can see how those ions then become hydrated, and this process continues with all the water molecules until it completely dissociates. Ionic bonds are also great conductors, but you can see in this diagram here, the picture to the left shows just pure water, which has no free ions, does not conduct a current. The picture in the middle shows the solid ionic structure. So we have table salt, and you see it does not conduct electricity either. As a solid form, those ions are not free to transfer electrons, but once you dissolve it in water, as you see in the right, then this compound does begin to conduct. Those ions are free and electrons can be passed through. But the main thing to remember is an ionic bond is made up of a metal and nonmetal, and if it contains metal, then it's going to conduct electricity, like all metals do. Other properties of ionic bonds is that they're very brittle. You can see this diagram in the top right. If a sharp blow is given to an ionic solid, you can see how those atoms shift and those like charges meet, and then that gives you some repulsion, and that instantly makes a clean break. And you can see the love story and breakup example below. Again, between a metal and a non-metal. So we like to equate the metal to the male and the non-metal to the female. All right, let's go ahead and now look at metallic bonds. You'll be learning a lot more about metallic bonds in other videos, but let's go ahead and look at the same types of properties pertaining to these. So you can see the formation is a little different. The atoms all become positive and just donate their valence electrons, and all these valence electrons just enter this, what we call the sea, or this pool of just free flowing electrons. So you have metal atoms bonding to metal atoms, and they're delocalized among these electrons, the sea of electrons. And you can see this here, the red atoms representing the positive metal atoms, and the negative electron shown here as just a negative sign, but just again, red atoms amongst the sea of electrons. Here's a picture of some precious metals, but of course you all know what most metal typically looks like, and of course we know it's solid. We also know the melting point of metals are going to be very high. You can see on the far right, your non-metals have a very low melting point, whereas the rest of the table, which is made up mostly of metals, have a very high melting point. We know metals will not dissolve in water, and we know metals will be great electrical conductors. They're also great heat conductors. Those metal atoms, those free electrons, are just able to pass those flowing electrons along. Copper, often used for electrical conduction. And of course, it's all metal, so metal conducts. Other properties include the fact that metals are malleable, like a mallet. They can be pounded or pressed. They're ductile, which means they can be pulled into wires, like the copper you just saw. And they're also lustrous, which means typically they'll have some kind of shininess or some kind of reflective properties. So that covers what we need to know about these two types of bonds and their properties. Thanks for tuning in.